Okay.
Okay. Okay. Thanks everyone for joining us today. Today we are hosting Jongmin Lee. Thanks a lot for accepting our invitation. Jongmin is a PhD student at the Seoul National University, advised by Ernest Ryu, and his research interest lies in optimization and reinforcement learning, particularly at their intersection, like he was telling us before, especially when he finds connection between fixed points in optimization and value iteration algorithm. He finds this particularly interesting. Thanks a lot for accepting our invitation, and the stage is yours. Thanks again.
Yeah, thanks. Thanks for kind explanation, kind introduction, and also I'm honored to be here to present my work. And thank you for all coming today. And I'm the Jongmin Lee, and I'm the PhD student in Seoul National University, and I'm currently working on the optimization and reinforcement theory. And particularly, I'm interested in intersection of those two fields. And title of today's presentation is Accelerating Value Iteration via Anchoring. And I believe both audiences are already familiar with the value iteration, while might be first time you heard about the anchoring. But don't worry, I will explain what is anchoring in later slide. But here, roughly speaking, the anchoring is an acceleration technique that has been widely studied in fixed point problem literature. And in this presentation, I will show that anchoring also provides valid acceleration in Markov decision process. So let me first introduce the what is anchoring and also what kind of setup it was studied. It has been studied. So for that, let's first study the fixed point problem. As the name of problem implied, fixed point goal of fixed point problem is to find fixed point given operator t. And here, operator t is a function whose range and domain are Euclidean space Rn. And of course, it can be generalized to the Hilbert space or general norm space. And to find fixed point x star, I denoted fixed point as a x star, and one might apply the Picard iteration, and which is defined as follows. To obtain in Picard iteration, to obtain next iterate xk, you apply the operator t to the current iterate xk minus 1. And repeat this every iteration. And interestingly, the convergence of Picard iteration is guaranteed by Banach fixed point theorem. This Banach theorem tells that if operator t is gamma contractive, here gamma is bigger than 0 and smaller than 1, then there exists unique fixed point x star. And furthermore, it guarantees the iterate of Picard iteration converges to x star with a linear rate gamma to the power of k. And this theorem is indeed powerful since it guarantees the existence of fixed point and also linear rate gamma to the power of k. However, there is one issue on this theorem, that is, it is not valid for the non-expansive operator. And if T is non-expansive operator, Picard iteration may not converge to a fixed point. As a counterexample, you can consider the rotation operator in the Euclidean space. And rotation operator has a fixed point as origin, but if your starting point is not the origin, then rotation operator never touch the origin, which is a fixed point, and rotation operator is non-expansive operator. And in that case, there exists a huge line of research to handle this issue, and one method suggested in this literature is a Halpern iteration, which is a main character in today's story. And Halpern iteration is defined as follows. To obtain next in Halpern iteration, to obtain next iterate xk, we add two terms. First term is beta k times x0, and second term is 1 minus beta k times t xk minus 1, And here, beta k is a coefficient we can freely choose, and x0 is a starting point, and xk minus 1 is current iteration. And here, we call beta k x0 term as the anchor term, since it has effect to pull the iterate toward the starting point. And you might wonder why this anchoring mechanism provide benefit on of the convergence. And this toy example might show some effect of the anchoring. This toy example is from the prior work written by my colleague Park and my advisor Liu. And this toy example consider the scaled rotation operator, which is in the Euclidean space, which is a contractive operator. And it also considers the 3 iteration. One is a Picard iteration, and other 2 is a Hoffman iteration with different coefficient beta k. In here, black line represents the trace of Picard iteration, and you can see that by the Banach fixed point theorem, this Picard iteration converges to the fixed point, and here origin is the fixed point, and it converges to the fixed point in a spiral. The blue line and red line all represent the Hoffman iteration with different coefficients, and it also converges to the fixed point in a spiral. You can see that this you can see that the Hoffman iteration shows more robust convergence, and also it converges faster than the Picard iteration. And this is due to anchoring mechanism. As I said in previous slide, the anchoring mechanism pull the iterate toward the starting point, which is 1,0 in this example, and it shows some valid acceleration in this scaled rotation operator. And this anchor mechanism has been widely studied in minimax optimization and fixed point problem. And specifically in Hilbert space, the Hoffman iteration, it was known that Hoffman iteration is exact optimal method matching the lower bound. And here lower bound can be constructed in the framework of the information-based complexity, but I will mention this later. And in general norm space, it was known that Hoffman iteration exhibits 1/k rate for any non-expansive operator. And these are indeed intriguing results. But however, I also just want to point out that these results cannot directly apply to the MDP setup, which is a Markov decision process setup. So for instance, the analysis in Hilbert space requires an inner product operation. But in discounted MDP, when we argue about the convergence of L iteration, the L infinite norm should be considered, and the L infinite norm is not equal with inner product. And for this reason, the analysis in prior works cannot be directly applied to this Markov decision process setup. So to tell the conclusion first, we succeeded to overcome this issue and obtaining some interesting results in this MDP setup by applying anchoring. The first, in discounted MDP, we obtain accelerated rate by applying Bell iteration. And for average rate MDP, we establish first non-asymptotic rates for in multi-chain MDP. And beyond the tabular case, in sampling setup with generative model, we obtain the best known sample complexity among the model-free algorithm. And from now on, I will explain these 3 papers in more detail. And the first, let me first explain the discounted MDP setup. And do you have any question, or should I answer? There are some questions on chat.
No. Ignore them. I think for now.
Yeah.
It's all right.
No problem. Yeah.
I think it's all pretty clear for now,
yeah.
As far as the intro is concerned.
Yeah. Let me keep going. So let's first discuss about the discounted MDP. And let me first introduce the background, the Markov decision process you might already familiar with. And Markov decision process, in short, MDP, consists of four ingredients: state space, action space, and transition probability and reward. And here, calligraphic M indicates the space of probability distribution over the state space. And we assume the single player or agent, and goal of player or agent is to find the good policy, and policy is defined as follows. And in this section, we consider the discount cumulative reward. Let gamma be a discount vector lies in between the 0 and 1, and define the value function as follows. And in the definition, in the bracket, you can see the infinite sum of discounted reward, and then take expectation over all trajectory induced by the transition probability and policy. And we also define the Bama operator as follows. And it was well known that the optimal value function Q star, which is a supremum of Q pi over the policy, is a fixed point of Bama operator. This equation, T Q star is equal to Q star, is also known as Bellman equation, and it is basically a fixed point problem. And also, it was well known that this Bellman operator T is gamma contractive with respect to L infinity norm. Now we are ready to define value iteration, and value iteration is a Picard iteration with a Bellman operator T, and can be defined as follows. And the following theorem demonstrates the convergence of the value iteration. And the theorem says that the VI exhibits the linear rate gamma to the power of k in terms of the distant solution, which is norm of the qk minus q star. And based on this result, we can also obtain rate on Bellman error, which is the norm of tqk minus qk. And it is also, Vi also exhibits the linear rate gamma to the k rate, gamma to the power k in terms of Bellman error. This theorem indeed is powerful because it guarantees the linear rate convergence of value iteration. However, it shares same issue, the case in the fixed point iteration, Picard iteration. That is, if gamma is close to 1, then it will show slow convergence rate. And to address this issue, the variants of VI have been suggested. And those are SAVI, Anderson VI, and PID VI. And interestingly, those methods are all motivated by acceleration technique in other fields. However, there is one limitation on these prior works, and that is to obtain the accelerated rate, they all assume some specific structural condition on transition probability. Specifically, they assume the certain reversibility condition or restriction on eigenvalues of the transition probability. And these conditions do not seem mild, since first, it is hard to verify whether this condition is satisfied, and assuming some structural condition on transition probability is not that easy. However, I will in the later slide, I will show that our method, anchor value iteration, exhibits accelerated rate without any assumption on transition metrics in terms of Bellman error. And this is our novel method, and this is novel method anchor value iteration, in short ANCVI. And this is basically same as the Hall penetration, but here we specifically choose a Bama operator T and also specific choice of beta k, which is 1 over gamma to the power of minus 2i from I is equal to 0 to k. And this choice of coefficient is motivated by prior works. As we can see, as the number of iteration k increases, this beta k decreases. And this implies that the strength of anchor mechanism diminishes as the iteration progresses. Now I'll present the main result of this section. And this theorem basically says that NVI exhibits the accelerated rate in terms of Bama error without any assumption on transition probability. I note that there is some condition on initial point, and I'll say this condition also have been used in analysis in variance of VI in prior works, and also if the real is the positive, then if the origin satisfies this initial condition. So this I believe that this initial condition is mild. And under this initial condition, NVI shows following rate. And if we see the last line in this slide, we compare the rate of NVI and rate of VI. And indeed, rate of NVI is always faster than rate of VI for any discount vector gamma. And one interesting point of this rate is that even if gamma is close to 1, our rate guarantees the sublinear rate 1 over k plus 1. In the theorem, if we see the equality part, then we apply the Taylor expansion on the previous rate and obtain the induced equality. And you can see that if gamma converges to 1, then this rate converges to 1 over k plus 1, which is some linear rate. And while the value iteration does show the slow convergence rate. And this is a part of proof, and the key step is denoted by the black triangle. And I just want to note that we utilizing the structure of Bama operator and Hall penetration, we obtain this. We perform this key step, and then through algebraic manipulation, we succeed to obtain the accelerated rate in the previous theorem.
Jamal, do you have a question?
Yeah, I do have a couple of questions. So one of the questions is for this rate. Like, it's a little bit hard to parse the rate. I do understand that as gamma gets close to 1, then a 1 over k rate is always achieved by this iteration, regardless of how close gamma is to 1. And that's a qualitatively different behavior than what you would see from value iteration without this Hopper trick or anchoring. But the original rate, like, besides that, like, okay, it's strictly smaller than this other one, like the final inequality over there, like, how much smaller is it? Like, it's like, do we, like, is there a more quantitative way of saying, like, how much, like, what is the gap between the two? Like, the ratio of them is going to 0 at some rate or whatever. I don't know. Like, have you looked into that?
First, I can, as you pointed out, if gamma is close to 1, then the rate of VI just roughly close to 1. On the left side, the rate of NVI close to 1 over k plus 1. So I would say in the region where the gamma is close to 1, there is some k vector difference.
Clearly.
Yeah. But I did not study.
Okay. So we don't know that. But okay, so another question, which is more like a general question. So this anchoring must have been studied in the general case, and the reason that, like, the anchoring must have been studied in the general case, and the reason that, like, the anchoring must have been studied in the general case, and the reason that, like, the anchoring must have been studied in the general case, and the reason that, like, the anchoring must have been studied in the general case, and the reason that, like, the anchoring must have been studied in the general case, and the reason that, like, the anchoring must have been studied in the general case, and the reason that, like, the anchoring must have been studied in the general case, and the reason that, like, the anchoring must have been studied in the general case, and the reason that, like, the anchoring must have been studied in the general case, and the reason that, like, the anchoring must have been studied in the general case, and the reason that, like, the anchoring must have been studied in the general case, and the reason that, like, the anchoring must have been studied in the general case, and the reason that, like, the anchoring must have been studied in the general case, and the reason that, like, the anchoring you can't use general results is because, as you mentioned, we need to rely on infinity norm, which doesn't have the inner product structure. And everyone who was studying this Halpern iteration basically assumes that the norm is compatible with an inner product structure. So there was no Banach space type of results available for Halpern iteration.
So yeah, but you're right about the research in Hilbert space. But there is also line of research in the studying the general norm space. But they in that case they only consider the non-expansive operator, not the contractive operator.
Okay, and then they have weaker results, I suppose, because the operator is not even contracting.
Yeah, this contractive condition is more stronger than non-expansive case.
And I'm like, you expect better results because of
right,
like faster convergence. Like for the non-expensive, they're happy if they converge in the limit, I guess. Maybe there will be no hits or whatnot. I see. Okay, that's really interesting. Okay, so regarding the proof, I didn't. So that was on the next slide. Okay, so you basically just go deep and use the structure in a very careful way, and that's how it happens. So we learned that this Halpern trick kind of works for this Bellman type of operators, but yeah, it's like would be hard to generalize for other operators, I guess, that are contractive. It's not like that if you have a contractive operator in a Banach space, then you have a general proof that would show that Halpern acceleration is, or Halpern iteration is going to accelerate things. Do you think that that's true, or we don't know?
I expect will be some positive result on the, even if you consider the general contractive operator, not only for BEM operator. I believe there we can get some positive results. But I will say that that our conversion rate might with high probability it will be better than the conversion rate from the general contractive operator, because in here I specifically use the some linearity of the BEM operator when the greedy policy is given. So I will say that we specifically use the structure of the BEM operator. So because of that, I believe this rate might be better than the rate from the general contractive operator, and that's my naive guess here.
Right.
Hi, so if I may interject, so hi, my name's Ernest. I'm a co-author of this work. Nice to meet you, Chaba. Yeah, so to add to Jongmin's answer a little bit, so the Halpern mechanism, which we are sort of rebranding as the anchor mechanism, is the same thing, just a different name. It's a quite classical mechanism. It's due to, of course, Halpern, and it's been around since the 70s. And when it was initially used, it was used for a different purpose. So the original purpose of this anchor or Halpern mechanism is to is when you apply a fixed point iteration, consider the fixed point problem in an infinite dimensional Banach space. You want to show.
Oh, your voice sound is cut off. Speak. Okay.
Can you?
Yeah, it's coming back. Yeah.
Yeah. So so traditionally, the Halpern mechanism was used to induce strong convergence in infinite dimensional spaces, because in infinite dimensional Banach spaces, from analysis, we know that the notion of convergence splits into strong convergence and weak convergence. So originally, the Halpern method was used for it was analyzed for uniformly convex Banach spaces, which excludes the this MDP setting because the L infinity norm is like not curved. So in any case, for uniformly convex Banach spaces, there has been a lot of prior work showing that, well, if you use this Halpern mechanism, you can make the weak convergence and make it a strong convergence result. So that was the use of the mechanism for decades. And actually, quite recently, it was discovered that if you use the anchor mechanism, you can actually use it to get an improved speed, a rate of convergence. So this was first discovered in the Hilbert space setting, as Jongmin mentioned, and then Jongmin's work is applying that technique in this Banach space setting where you don't have access to an inner product, and also because the norm is not uniformly convex, because it's a L infinity is like a very straight fielding norm. Jongmin has to rely on certain monotonicity arguments to make the proof work out.
Thanks. That's useful.
I think that
Okay, Jongmin.
yeah. So let me keep going. And so this this slide is about the complex lower bound, but because of lack of time, I just briefly explain. I just want to point out that this complex lower bound basically says that if your algorithm satisfies the span condition, then your theoretical conversion rate of your algorithm, your method, cannot be faster than this lower bound. And this is what this lower bound basically say. And I just also point out that the anchor value iteration, anchor VI, and also standard value iteration satisfy this span condition. Hence, those conversion rate cannot be faster than this lower bound.
Yeah.
But yes.
So usually this span condition comes up with analyzing gradient type of algorithms, whatnot. And the result is this type of result that says that if the dimension is large enough, then basically you have, like, you are scaling the dimension or the size of the problem together with the number of iterates, right? Like, it's not like you have a fixed problem and with a fixed dimension, and then you are showing results on that. It's kind of like this very transient kind of behavior. I guess this is the same, right? Like,
yes,
I couldn't parse the whole thing, but
yes, as you point out in here, in this term, you see that the n, which is the dimension of the MDP, was bigger than the k plus 2, where k is number of iterations. So the dimension depends on the number of iterations. So you're right. You're
it basically says that you have to collect information about all the states or something like that. I don't know.
Right.
Yeah. Okay.
Yes.
No. That was a mistake.
Yeah. So based on this truth theorem, we now can establish the optimality of NPI. So by briefest, if you see this inequality, the left term indicate the lower bound, and middle term indicate the rate of NPI, and right term indicate the 4 times lower bound. And this inequality says that our NPI is optimal up to constant of vector 4 by matching the lower bound, while the value iteration is suboptimal. So to summarize this section, and so in this section we show that the anchoring mechanism also provide valid acceleration in discount MDP setup, and specifically NPI reduce the Bellman error faster than VI, and it is optimal method up to a vector for by batching the lower bound. And in the paper, we also show that this anchoring mechanism provides the same benefit in the approximate VI and Gauss-Seidel VI setup as well. Yeah, and those are all about the discount MDP. Now let's move to the average reward MDP. But average MDP, if you don't have question.
Yeah, we can move.
Yeah. So yeah, let me first define the average reward MDP. So in average reward MDP, we define the average reward of given policy as follows. So in the bracket, you can see that sum of the reward without the discount factor. So we don't need discount factor anymore. And instead, we take the expectation and then divide it by t. And then take a limit, send t to the infinity. That's how we define the average reward of a given policy. And this is critically different from the value function in the value function in discount MDP. And also, we define Bellman operator as follows without the discount factor. And in average reward MDP, the class of MDP is important factor in analysis. And there exists the three class of MDP, and one is unichain. Those are unichain, weakly communicating, and multi-chain MDP. And there also exists a clear inclusion. And you can see in the figure, the unichain MDP is a weakly communicating MDP, and weakly communicating MDP is a multi-chain MDP. And we use the multi-chain and general interchangeably because every MDP is multi-chain MDP. And class of MDP, as I said, class of MDP is important factor in analysis of average reward MDP because class of MDP determines the structure of Bellman equation. Let's see what this actually means. So first, let's study the weakly communicating MDP. And I denote the definition of a weakly communicating MDP in the footnote, but rather than focusing on the definition, it is better to study the Bellman equation because that is what we actually use in the analysis. So in the weakly communicating MDP, Bellman equation is defined as follows. And if you see this Bellman equation, you could find the two variable, h and g. This means that if we want to solve this Bellman equation, then you should find the two solutions satisfy this Bellman equation. And this Bellman equation is not the fixed point iteration, fixed point problem anymore because h is not the fixed point of this equation. But it was known the solution of the Bellman equation G star is the optimal average reward, which is a max of the G pi over the police pi. And also the police pi attaining the maximum in the Bellman equation is an optimal policy. And one advantage of weakly communicating MTP setup is that G star, the optimal average reward, is a uniform vector, which means that every coordinates are same. Now let's move to the multi-chain MDP. And in multi-chain MDP, Bellman equations are defined as follows. And it looks interesting. It looks interesting and become more complex because now you have two Bellman equations. And the second Bellman equation is the same one in the weakly communicating MDP, but the first one is new. And this means that to solve this Bellman equation, you should find the two solutions G and H which simultaneously satisfy this two Bellman equation. And this is why analysis in average reward become more complex than analysis in the discount MDP. And similarly, a solution of this Bellman equation G star is optimal average reward. And by solving this Bellman equation, you can obtain an optimal policy. And in this section, in this average reward MDP, we consider the two performance measures.
So wait, quickly, Jongmin.
Yeah.
There's just a question in the chat about the spam condition, but I guess it remains the same in the average reward case, right?
Yeah, yes, it will. I will show in later slide, and so I will clarify this later. So, and the answer is yes. The spam condition also remains same for average reward MDP.
Yeah, thanks.
Yeah. So here we now consider two performance measure, and one is Bellman error, and another is policy error. And a slight modification is needed in the average reward MDP because in here we define the Bellman error as a norm of TV minus V minus G star. And we need additional term G star to define the Bellman error, and you will see why soon. And also you define the policy error as a G star minus G pi V, and this quantify the how good policy is by estimating difference between the G star and the average reward of your policy. And it was known that there exists an interesting relationship between the Bellman error and policy error. And following facts demonstrate that relationship. And this classic result says that in a multi-chain MDP, if the Bellman error achieves zero, then the policy error also achieves zero. This means that if you find a value which makes the Bellman error zero, then policy induced by the value is the optimal policy. And furthermore, if the MDP is weakly communicating, there exists a strong relationship. That is, policy error is always smaller than the Bellman error. And this implies that if you obtain the rate on the Bellman error, then that directly leads you to the rate on the policy error. And this is a good news because in discounted case, we show that anchoring mechanism effectively reduce the Bellman error. And if it occurs same in the average error MDP, then we can achieve both small error and policy error. For introducing our main result, I will introduce the prior result on convergence of value iteration. And for the average reward value iteration is also defined as a Picard iteration with Bellman operator T. But this is no longer fixed point iteration. And classic result says that in general MDP, assuming some periodicity condition on the transition probability, then the Bellman error of the VI converges to zero. And furthermore, the policy error also converges to zero. And this is an interesting result because even though the value iteration is not the fixed point iteration, it guarantees the convergence of the both Bellman and policy error. However, there is one issue on this result, and that is this result says nothing about the convergence rate. And to the best of our knowledge, the non-asymptotic rate in multi-chain MDP remains unknown, since this classic result only guarantee the asymptotic convergence of value iteration. And as we expected, by applying the anchoring mechanism, we succeeded to obtain non-asymptotic result rates in the multi-chain MDP. And this theorem says that in a general MDP, our anch value, our anch BI exhibits the non-asymptotic rate in terms of Bellman error and also policy error. And so first, I note that we use anch BI with the choice of beta k 2 over k plus 2, and this choice of beta k is inspired by the prior one. And if you see the inequality, the left term is policy error, and the middle term is a Bellman error, and in the right term, those are constant term multiplied by 1 over k plus 1. And indeed, this inequality show that our NBI exhibits the non-asymptotic rate. However, there is some requirement. Yes, Chaba?
Yeah. Well, I let you finish.
I see. So let me finish just explanation for this slide. So yeah. It's the one requirement on the number of iteration. So this capital K is defined as follows in the bottom of the theorem, and the capital K depends on the epsilon. And epsilon is defined by infimum of the norm of the p pi g star minus g star over some specific class of policy. And roughly speaking, this epsilon quantifies the deviation of the suboptimal policy in terms of the first Bellman equation. I remind that the first Bellman equation in multi-chain MDP was the P pi G star is equal to G star. But here in this theorem, we first show that we show that epsilon is always bigger than 0, and hence the capital K is always finite. And since this capital K depends on the structure of it is determined by determined by the probability transition probability. So this rate is indeed a non-asymptotic rate. Yes, yes, I finished.
Okay, well, that's a bummer, right? I mean, it's great that it's non-asymptotic, but the transient up to the first K steps, capital K steps, is like whatever, we don't know. And the epsilon can be arbitrarily small. You just introduce some policy which is like very close to optimal, and it's not optimal. So it's like, oh, okay. But I actually had a different question. So here you're using this beta of K, which is like inverse linear. It's like 1 over K type. And I was wondering whether for the discounted K you can use the same and get similar result, like a 1 over K type of result.
Yeah, I believe maybe that would be a possible direction, but I never tried it. But I believe it will work for because in gamma quadratic case you can choose whatever you want, and I believe it also works for it will give some positive converse rate for this choice of beta K, I believe.
Okay. All right.
Wait, so I have another question on the epsilon. So when the gain is constant, like this epsilon is like the set over which you're taking the infimum is empty, no?
Yeah, that just let me explain next slide. Yeah. And so yeah, fortunately, we can avoid this issue of number of iteration by focusing on specific class of MDP. And this corollary says that if the general MDP satisfy P pi G star is equal to G star for any policy, then NBI exhibits the clear sublinear rate. So if you see this inequality, then it shows in the right term it is 8 over K plus 1. This is some near conversion rate, and it does not require it does not require on number of iteration. And weakly communicating is satisfy this condition, because as we said before in the weakly communicating slide, the G star in weakly communicating MTP is a uniform vector, which all coordinates are same. So this condition P pi G star is equal to G star is automatically satisfied. So this clear sublinear rate is also valid for the weakly communicating MDP. And this is a proof. This is part of proof. And honestly speaking, in this proof, it's hard to determine the key step. And I want to say, I just note that again, utilizing the structure of a Bellman equation, and this is important. Bellman equation, also Bellman operator, and incorporating with the Halpern iteration, and and also through the use of algebraic manipulation, we obtain the prior converse rate in the prior theorem. And for the average rule of the MDP, we also obtain the complexity rule bound. And for the unichain MDP, we establish following 1 over K plus 1 rate. And using this complex bound, now we can also establish optimality of NVI for weakly communicating MDP. So by previous two theorem, we can present the inequality where the left term is a lower bound and the right term is a rate of NVI. So this implies that NVI is optimal up to a constant of vector 8 in the weakly communicating MDP. since unichain is the weakly communicating MDP. To summarize, for this, we also show that anchoring mechanism is also valid. It provide acceleration for average world MDP. And specifically, we first established 1/k non-asymptotic rate on the Bellman and Police error for multi-chain MDP. And furthermore, for the weakly communicating MDP, we established the optimality of ANK-BI, which matches the lower bound by factor 8. Yes. So from until now, I talk about the tabular case, which we can assuming that we know exact the transition probability exactly. So now let's move to the sampling setup with the generative model. And do we have any question? If not, then let me keep going. Let me go ahead. Or yeah. So generative model, which provides independent samples of the next state for any given initial state and action, has been widely studied in the RL theory literature. And here we assume the reward is known. And the main task in this generative model setup is to compute the epsilon optimal policy, which is just the norm of G star minus G pi is smaller than epsilon. And there in this setup there exists two classic approach. One is a model-based approach, and another is the model-free approach. Model-based approach is to approximate the transition probabilities by sampling and build a surrogate model, and then solve surrogate model by the dynamic programming technique, like a value iteration. In contrast, model-free approaches attempt to recursively approximate the value or policy, and thus the advantage of this model-free method is that it requires lower memory, and it can be combined with the function approximation technique for large-scale problem. And there is a line of research to obtain efficient sample complexity in this generative model setup. And it was known that in this kind of setup, both model-based and model-free method achieve optimal sample complexity by matching lower bound. However, in average world MDP setup, it was known that the model-based method achieved the optimal sample complexity, but the model-free method still exhibits a gap with respect to the lower bound. And furthermore, there is one issue, and that is most methods, including model-based and model-free, it requires a priority bound on the span seminar of the B spectral H star. And here, B spectral H star was the solution of the Bellman equation. And these are the table. They list the prior model-free method for weakly communicating MDP, and in this section we consider the weakly communicating MDP. And in here you can see the sample complexity, which number of sample to obtain the epsilon optimal policy, and in the prior knowledge column it indicates whether method use prior knowledge of the H star. And you can see that more than half of the methods use the prior knowledge. And as we have done until now, by applying the anchoring mechanism, we obtain some interesting results. And first, we suggest a new novel framework, which is the Sabia Plus, and we show that Sabia Plus achieve best sample complexity among those model-free methods without prior knowledge of span seminar of H star. And you can easily check that if you see compare the sample complexity in this table. And our now I introduce our framework, and it is consist of two main parts. And first part is obviously anchor value iteration, but here we consider the span semi-norm instead of the L infinity norm. In the previous section, I showed that in the weakly communicating MDP, the anch VI exhibits following clear some linear rate. However, even if we consider the span semi-norm, we can obtain similar rate. In the last inequality, you can see the left term is a policy error, and the middle term is span semi-norm of Bellman error, and the right term is the 1 over k plus 1 rate. And the important difference with the span semi-norm and the L infinity norm is that in span semi-norm, we don't need G star anymore to compute the Bellman error. So in the span semi-norm of TQK minus QK, there is no G star. And this computability of the Bellman error, later I will show that this makes our method no longer require a prior knowledge. And I will clarify this later slide. And another main also, how do you obtain the second is it needs some calculation. Yeah, I didn't describe here, but I described it in my paper. Yeah, so I'm sorry, it's hard to but I will say that the analysis is basically the same, because when we analyze L infinite term, what we I think it's better to discuss with the paper, so maybe it's hard to argue here. Yeah. Yeah, then let me keep going. And in this, in the second part of the framework is the recursive sampling. And here, I must clarify that this calligraphic T indicates the real Bema operator. What I mean by that is that now we are in the sampling setup, so it is impossible to calculate the Bema operator exactly. So now I'll denote the calligraphic T as the real Bema operator, and just the normal T as our empirical Bema operator. And in this generative model setup, one natural approach to approximate the output of Bema operator is just use naive sampling. And naive sampling is approximate the output of Bema operator by collecting the sample from the generative model and add all the Q value on that sample state, and then add all them and then average it. And by this naive calculation, we can approximate the output of Bellman operator. However, to reduce the sample complexity, to obtain an efficient sample complexity, in this paper we use a recursive sampling. And recursive sampling approximate the difference between the consecutive output of Bellman operator TQK minus TQK minus 1, and add it to the previous approximation TK minus 1. And the intuition of the recursive sampling is that instead of approximating TQK, we by approximating the difference between the two consecutive iterate, we reduce the number of samples to calculate this this estimate. And it can be formulated as the follows. And through this framework, I present our stock code of our framework, our method Savia, and Savia stands for the stochastic anchor value iteration for average word MDP. And if you see the for loop, then the first line is about the anchor mechanism, and then after that, those lines are about the recursive sampling. And then output is Qn, which is value, and the Tn is the approximation of the output of BEM operator, and pi-n is our policy. Yes, Chaba?
What is MK here?
MK
Well, that's a
is
number of samples. Yeah.
Yeah. Number of samples. Yeah, exactly. Yeah.
And so
MK,
you have an input target precision epsilon.
Yeah, epsilon
right?
and number. Yeah, right.
Okay. And what is alpha? Alpha is there. CK is there. These are just, yeah, okay. Okay. So you're adaptively something more or less. Okay, got it.
So now let me present the sample complexity of Sabia, and this is one first main result. And here we assume that reward lies between the 0 and 1, and also the span seminar of H star is bigger than 1. And I just want to mention that this condition on span seminar of H star is for the comparison with the prior works and lower bound. In the paper, we also suggest the sample complexity without this assumption. So you can check this in the paper. And also let Qn, Tn, Pi-n be the output of the Sabia, and with the Q0 is equal to 0 and epsilon is smaller than 1. Then this corollary says that with probability 1 minus delta, we have following convergence rate, and also we have following the sample and time complexity. And this conversion rate, we can say this is kind of stochastic version of the result in the previous section of the weakly communicating MDP. And this corollary holds for arbitrary n, where n is the number of iteration. And if we set n is set to the span seminar of H star over epsilon, then it produces a 12 epsilon optimal policy with the following sample and time complexity. And as we showed in table, this sample and time sample complexity matches the lower bound with the span seminar of H star. And furthermore, this is the best known sample complexity among the model-free method. However, there is an issue in Sabia, and as we showed in previous slide, Sabia is indeed effectively reduced the Bayman and policy error. However, in previous slide, I showed that if we set n to span seminar of H star over epsilon, then we got the 12 epsilon optimal policy. That means that we need the information of the span seminar H star to determine the number of iteration. And this is not good news, and we want to avoid this issue. And using the doubling trick and stopping rule based on the empirical Bema error, we can overcome this issue. And this is our main method, Sabia Plus. And first, I note that in the input of Sabia Plus, there is no number of iteration. And for every iteration in the for loop, you can see that ni is set to the I. So for every iteration, we increase number of iteration by power of 2. And then run the Sabia inside. And we perform this for loop until span seminar of Tni minus Qni is smaller than 14 epsilon. And this span seminar of Tni minus Qni is an empirical Bellman error. And I believe this is a special, good property of Bellman error, because if you consider the distance solution, which is the norm of the bk minus b star, then to compute that quantity, you need some information of the b star. Even if you consider the policy error, which is the norm of the g star minus g pi, then you also need information of the g star. only this empirical Bama error doesn't need any information about the MDP, because MDP. And incorporating with this computability of empirical Bama error, we can use this explicit stopping rule, and this will our method no longer require any prior knowledge. And this is our last main result, which is the sample complexity of Sabia plus. And under the same condition, this corollary says that with 1 minus delta probability, we can obtain the epsilon optimal policy with the following sample complexity. Again, this algorithm does not need any prior knowledge of span-seminal H star due to the doubling trick and the computability of empirical Bama error. And also, this is the best known sample complexity among the model-free method, and it matches lower bound with span-seminal over H star. And the two key lemma to prove to obtain the previous result. There is two key lemmas, and first lemma is basically said that under our setup, with high probability, the TK, which is the empirical output of Bama operator, and real Bama output of Bama operator, which is calligraphic TQK, is not that different. It always small. That span-seminal of difference is always smaller than epsilon simultaneously for all k. And basically, based on this first lemma, the second lemma says that under the if this difference is not that big, then the difference between qk and qk minus 1 is also small. And I want to remind that this qk minus 1 was appear in I explained the recursive sampling. So this lemma says that since the qk minus 1 is small, then due to the recursive sampling, we effectively reduce the sample complexity. Yeah. So to summarize, in this section, as we have done until now, we show that anchoring mechanism also provides some valid benefit on this sampling setup with the generative model. And our new method, Sabia Plus, achieves sample and time complexity following sample and time complexity, and it matches with the lower bound up to constant vector span-seminal H star. And this is best complexity among the model-free method, and it does not require any prior knowledge. And in the paper, we further study the expected sample complexity, which is widely studied in the multi-arm banded literature, and also we extended this framework to the discounted MDP. Yeah, so now let me conclude this presentation. And in the first section, I introduced what is anchoring and in what setup this anchoring mechanism has been studied. And basically, it has been studied in fixed point problem and minimax optimization literature. And in that literature, anchoring mechanism provides a valid explanation. In those series of work, me and coworker show that anchoring technique is also valid for MDP setup. And in inspiring this success, we hope that this anchoring mechanism can be extended to more various setup and provide valid benefit on this reinforcement learning field. Yeah, this is end of my presentation, and thank you for listening.
Thank you very much.
Very nice.
So maybe I have a naive question,
Sure.
but so I don't really have a good intuition as to why the anchor mechanism helps. And to me, maybe a more natural setup, if I had to think about one, would be to have the anchor as being the previous iterate, because anchoring with the Q-1.
That is known as cross-skill man iteration, and it's also Q-learning, right? And that the anchor with that, is that what you said? So xk is equal to beta k xk minus 1 plus t xk minus 1, and that is called km iteration in the literature of fixed point problem. And that is also widely studied, and it already applied to the Q-learning because it has some effect to stabilize the randomness in the sampling setup. So
right, yeah. And so for this scheme, I guess you could also see it as applying an aperiodic transformation to your MVP.
Oh yeah, of
by
course.
adding loops. So is there like a similar interpretation for the anchor update?
I would say that for the average rate MVP setup, not this generative model, but in the tabular setup, in our paper, we also consider the convergence of KM iteration. And for KM iteration, it shows that 1 over root K rate, while the Halpern iteration exceeds the 1 over K rate. And yeah, so it showed that KM, although yeah, that was written in our paper.
Okay, I see.
Yeah,
thanks.
I had the related, yeah. Well, maybe Ernest, you can comment.
Ernest, you are mute now. I can hear you. Yeah.
Sorry for. Okay, I think my mic is working. Sorry about that. Yeah, so maybe I might add something to Jongmin's answer. So I think maybe the broader question is that the anchor mechanism feels a little bit unintuitive, and it's unclear why this should help. So kind of going back to how the anchor mechanism was discovered and how this use was discovered. Originally, again, the anchor mechanism was used to induce strong convergence in the setting of Hilbert spaces and Banach spaces. And if you read that proof is kind of intuitive. But in any case, that's not the use that we're using. That's not why we're using anchoring here. We're using anchoring because it allows us to prove a faster rate. The very initial proof that shows anchoring is helpful, that it induces a faster rate. It was done in this reference number 8 by Leader in 2021. And this proof was actually discovered with the aid of computers. So this was a computer-assisted discovery of the proof. I won't get into the details, but you solve a semi-definite program to help you find the proof. So that is to say that the proof was not discovered by sort of human intuition or ingenuity. It was discovered with a computer, and then we are kind of reinterpreting what the equations mean. So that is to say that the proof that goes into utilizing the anchor mechanism to get a faster rate, in my view, feels quite unintuitive, even to me. Maybe Jongmin has a better sense of intuition, but to me, it's still a very unintuitive mechanism because, well, if you have an iteration, the whole point is that you start at somewhere and then you want to get to the solution, which is not at the starting point, but you keep pulling the iterations back towards the starting point, and that does feel quite unintuitive. There are some examples where the mechanism kind of helps and dampen like some certain cycling effects, but it's not quite clear why this should be helpful. Although I will say that if you initialize your algorithm at 0, then you can interpret this anchor mechanism as basically doing weight decay. Because in trained neural networks, you do weight decay, meaning you shrink your parameters back towards 0. So you can kind of interpret anchoring as it is shrinking your parameters back towards the starting point, and if it's at 0, then it's kind of like a weight decay. But again, so to me the proof sort of structure is still quite mysterious and unintuitive, but it works, and it's also been working in several different areas of optimization. So there's this one, and then I won't get into the others. There are a handful of other applications where the anchor mechanism allows us to prove tighter and better theoretical rates, and Jongmin's contributions are in that line.
Yeah, I have a related question/comment, which was that maybe there is something in between that. Well, I don't know. Maybe we shouldn't resist Halpern iteration. Maybe it's the greatest ever way of accelerating this iterative fixed point computation methods. But like again, like going after intuition, one would think that sometimes updating this anchor point would be useful, right? Like, so I don't know whether, like time to time, you could think about that. Oh, like this is time to update the anchor point. So looking at the proofs and with your experience, do you think that there is something there, or that's just a dead end and we should just stick to Harper iteration?
Your question reminds me there is some restarting technique. So
Yeah.
in also Hopper iteration, there I believe in the not in this literature, but in the Hilbert space literature, there exists some line of research that study the Hopper iteration with the restarting because the maybe
Yeah.
the same reason with you. But yeah,
Right.
yes, but I'm not
The only thing,
normal.
yeah, the thing that comes to mind though is that like you had in one of the theorems at least some condition on the initial iterate, where you said that if the reward is non-negative, the condition is obviously met with the zero vector. So that's all good, but that condition will not be met once you are doing this restart. And then, like, who knows what happens? Like, it's a little bit unclear what's going on here. Maybe another view of these operators, that these operators have monotonicity properties. They're interacting with the identical one function in a nice way. So they have these specific properties. So maybe one can design something based around that, and then obtain something that's a slightly more general view, and that could help with getting closer to understanding what is going on here. But another thing that I wanted to ask, which is related to this, is whether you actually tried any of this on any problems, numerical simulations, whatnot, and what's your experience with that?
Yeah. I tried some numerical experiment with a very toy example, like a cliff
Yeah.
work and maze, and also the what is that? Oh yeah, I forgot the name, but I just tried the toy example, and honestly speaking, with this choice of coefficients, the the experimental results are not that promising, which means that the value iteration, most of the time value iteration show better empirical conversion rate than the anchor value iteration. And of course, for the worst case example that we established in the complex lower bound, our anchor value iteration is faster than the, the faster than the value iteration. But for at least for the example I tried, experiment, it does not provide some some promising accelerations. So and we also consider, because of that, we consider some but that is for Halpern iteration with the choice of beta k 2 over k plus 2. So if we adaptively find beta k for every iteration using the previous information, and we guess it might give the better conversion rate, and this is just my expectation, and this is called adaptive harmonization. But for at least for this harmonization with this specific choice of beta k, experiment is not that promising.
So this adaptive choice of beta k, it sounds intriguing. What is the basic idea there? What do you optimize to choose beta?
Yeah, that's the current there's the proceeding work, and in there it's based on and then we should see the proof, because when to define beta k adaptively, then you should define beta k based on the previous iterate. And if you see the analysis is this Harper iteration, then you can, how to say, you can decompose the txk minus xk with the previous some term related to previous iterate, and based on the previous iterate, we can solve the optimization problem. If we know all the previous term, then each terms are specified, and using that specific value, we can solve optimization problem with respect to beta k. Then we can adaptively obtain a beta k by this analysis, and that's the basic idea in the adaptive of Harper iteration.
So it would basically optimize the Bama residual or something like that?
Yeah, but optimize beta k, because we should optimize.
Yeah, you're optimizing beta k is a free parameter.
Yeah.
But what is the objective that you're optimizing?
Oh, there is a in my it is the Bama error.
Yeah, okay.
Yeah, TXK minus XK.
Yeah. That's what I saw. Okay.
Oh, yeah.
Yeah, sounds good. All right, interesting. And so have you tried experiments with the optimization, like the optimized beta K?
No, that's one of our
Not yet.
future directions. Yeah.
Okay. All right. Okay. Sounds good. Well, I wish some of these ideas would lead to some actual improvements, but it seems that some further work needs to be done for that to happen, because even though there is an improvement in the worst case, maybe there is a price that is being paid here on other instances, which is quite interesting. Yeah.
Thank you for your comment. Yeah.
So are you planning to extend it to like the online setting at some point?
Yeah, that's also our one of future direction to consider the asynchronous update setting is also open problem that whether this anchoring mechanism works even in the hyperspace case. So that will be very interesting future direction.
Nice.
Regarding the algorithm that was presented at the end for the average case MVP, or the generative model, actually. Sorry. Yeah. So it seemed that there are two main ingredients: the Halpern iteration, and also kind of this momentum or acceleration term or whatnot for variance reduction. So which of these two are more important, or like both are equally important, or what do you, how do we think about this?
So I'll say that so as you imagine, both two techniques are important, but I can say this. So if you this you can if you see this conversion rate on the corollary, then in the most right term there is 8 times span same over h star over n plus 2 plus 4 epsilon, and this in here the epsilon comes from the approximation error, and the h star over n plus 2 comes from the convergence of the anchor value iteration. So recursive sampling reduces the approximation error, and the anchor value iteration reduces this error with respect to h star. So that's the basically role of these two ingredients.
Right. They're working together.
Yeah.
Okay. It's kind of just like a little bit muddy, because with that variance reduction, the whole, so it's not Picard iteration anymore, but like some kind of momentum or acceleration is going on there too. And now you're doing Halpern on the top of that, basically. Right.
You can say it's Halpern iteration is generalization of Picard iteration, because if we set beta k to 0, then it is just Picard iteration. So if we don't use anchor term, then it is just Picard. So yeah.
Okay. All right. Thank you.
Maybe I should stop the recording.